So welcome. This is the section which is on diffraction and polarization. It's the last section in the course. I'm going to come down here and get my pen and say pen, and then okay, let's go through here. So basically, what we have here is good old Fraunhofer and Fresnel diffraction. And basically, if you have an opening and it is relatively close or not too far away from a screen, then what I will not see is just a circle of light and darkness. I will see a circle of light with a series of rings around it. And these are diffraction effects, sometimes called an iridesque. And if I look at the intensity of light, if I draw a line through this pattern, look at the intensity of light, I can see that the minimums don't go quite back to zero. If I were to move this a long, long way away, then I would see a pattern that looks more like this, where the minimums do go to zero. And if I was to look at this, so if I was to look at this in intensity, I'd see a pattern that looks like that. Alternatively, if I can't move a long, long, long way away, I can fool the light into thinking I'm a long, long way away by having a converging lens there. And so what I then see is this pattern. So Fraunhofer diffraction involves this distance being incredibly far or having a lens there. And Fresnel diffraction involves not being incredibly far and not having a lens there. And all I need for you to do is to be able to know the difference between the two. Know the two terms, know the difference between the two. That's as far as we go. If you do more with optics, you'll do more about this. The important thing, I guess, is to recognize that because of diffraction, edges don't give you sharp distinctions between light and dark. When you look in detail, even an edge with nothing at the other side, like a razor blade just stuck halfway across a laser beam. If you were to take a photograph of it, you would see the darkness that you'd expect, but there'd be a whole series of fringe lines inside what should have been the air, the lighted part. And these really do mess with you. If you were looking at stars, because of the edges of your telescope, you wouldn't see spots of light. You'd see like little pimples of light with rings around them. And the narrower your telescope, the more significant these effects are. And it's a real pain. And the way you get around it is you get more light not near the edge of your lens. Well, that's not right. That's not a good way of saying it. Rather than having a little telescope, I have a big telescope. And so more of the rays, another thing that I need to tell you is you don't really want to use the very edge of any lens because it's always distorting. But this is a very narrow gap. And so proportionately I get a bigger diffraction effect with a telescope like that than I would do with a telescope like that. Both have diffraction effects, but the diffraction effect is much smaller with a wider telescope. So wide telescopes do a couple of things for you. Number one is they improve your resolution, as we'll get to later with the Rayleigh criterion. And number two is they enable you to see less bright objects. So those are the two things that wide telescopes do that narrow ones don't do. Magnification is just the lenses or the curvature of the mirror. When you see a cheap telescope, they'll always put a big magnification on there. Say, look, this can magnify 200 times. And yes, the lenses will give you a magnification of 200. You're not going to see much through it because the chances are that the telescope is very light and will bounce around. So it's like looking at a very narrow field of view and then bouncing it around. So it's an awful thing to use. There's nothing worse than a really cheap telescope. They don't work. So you look for a wide telescope with good resolution. So then we talked about diffraction gratings, and basically I don't want to dwell on this that much. Basically all I need you to know is that, and I do homework questions on it, but I've tended to drift away from the homework questions over time. But basically m lambda equals a sine theta, where this is the value of A. The A is not the distance between the slits, but it is the width of the slit. And notice that this is for destructive interference. So it's backwards, it's different, it's easily confused. So know that this exists, be able to draw the diagram and talk about it, but I would not be, this would be a very low priority choice for me on a test this time around. The outcome of this is that you get not these spots, but you get a spot with a ring around it, and this is really important. So if I have two stars that are well separated in terms of an angle, then I can easily see them, because even though there's rings around these things, you can tell that there's two stars there. On the other hand, if I have two stars that are closer together, I start getting more and more overlap, and I get something like that. And I can see there's two stars there, but only just. And if they get any narrower, then I in fact can't tell there's two stars there. So I need to be able to distinguish between an unresolved image and a well-resolved image. So I need to decide what's just resolved. And it's just resolved when the crest of the red light sits on top of the minimum, the first minimum of the green light on that diagram. Just resolved. So know the terminology well, just, and unresolved, and then be able to tell me the criteria for the resolution. Oops, wrong way. No, right way. If I take this and I analyze it, I can actually determine, and this is what I'm interested in, that the minimum angle that two stars have to be the minimum angle that two stars can be and still be recognized as two stars is given by the Rayleigh criterion, which is that minimum angle is 1.22 times lambda. Lambda is the wavelength over d. So one thing to recognize is that your telescope has different resolutions for different colors. Now, because there's not that much difference in wavelength between one color and another, you don't notice that the blue is really blurred but the red is really sharp, or vice versa. But radio waves have a real problem been resolved, because lambda's like kilometers rather than nanometers or hundreds of nanometers. So if I want to have a good resolution with a telescope, with a radio telescope, I need to have a dish which is, 100,000 times bigger than an optical telescope. And they make them bigger, but not 100,000 times bigger. So what they've started doing is having radio telescopes connected in parallel to each other. And this is a bit like taking a lens and throwing away the middle bit and keeping the outside ring. And it still works as a lens. It's not as bright, but it's still got that resolution because of the width of the lens. You don't need every part of a lens for the lens to work, just like you don't need every part of a mirror for the mirror to work. So the trick is take a relatively small radio telescope on one end and put the relatively small radio telescope on the other, but have a big distance between them, and it's got much better resolution than either one by itself. Now, you've got to connect them real time, so you've either got to timestamp the signals that you get with a very high precision in time, or you've got to actually real time connect the two of the detectors together. You can't just take a picture with one and a picture with the other and then kind of compare them. You got to basically sync the data. So first of all, wavelength has a big effect, and then diameter has a big effect. If I want to buy a better resolving telescope, I buy one with a smaller angle. Smaller is better. Okay. So that's Rayleigh criterion is like really important. And then we come to diffraction gratings, and this is kind of really, really important. We did the experiment. Well, we didn't do the experiment, but we did the discussion where we had the light source and we had a prism, and we got the dispersion of the colors of light, and then we used a telescope. This was a spectrometer, very standard lab equipment. And these days, what they do is they basically put all this in a box, and they can get a spectrum out through a computer. They have a big multi-channel detector rather than an eye, and they get an electronic signal out which gives them a spectrum. Yeah. And what this enables you to look at is it enables you to look at the light in detail. You can tell exactly what colors these are. This is not just red, but a shade of red. This is a different shade of red. This is an orange. You can be very precise. Ratios matter. So I can get virtually a fingerprint for a different light source. And if the light source is created, if the colors are created by, say, a flame test or a star's fusion, I can do some detailed analysis of what's on the star and what's around the star. This has been a tremendous breakthrough over the last, well, certainly spectroscopy for the last 100 years, but it just gets better and better. The resolution gets better and better and better, and the sensitivity gets better and better and better. And then the computer deconvolving of complex spectra gets better and better and better. So, for example, I can't remember if I told you this, but there's a spectroscopist who's basically predicting that we will detect if there is light on another planet, if there is life on another planet, by looking at the spectrum of light from that planet. And about 10 years ago, he said we were 20 years away from finding it, and he's probably right. We're just getting better and better at this kind of spectroscopy. There's an edge. If you look at these peaks, there's little edges on them sometimes, and there's an edge which is associated with vegetation. Could be pond scum, could be conifer trees, but it's vegetation. And if you see that, you know there's vegetation, and that planet. He also said if you want to advertise to your neighbours that you're around, put osmium in your put technetium, I think it was. Put technetium in your upper atmosphere. Because technetium is one of those elements that don't occur naturally. And if it doesn't occur naturally on Earth, chances are it doesn't occur naturally elsewhere. You'd never see it. You've got to make it. Well, technological societies make it as far as we can see. So you want people to know you're technologically advanced, put technetium in your upper atmosphere. It also says there's animals there. And if they treat us like we treat animals, then, I'm not looking forward to being visited by more advanced life because, at best I'll be a pet. And I might actually be like, a sandwich. It's like so. Well, wouldn't it be nice if we could do something a bit more advanced than the piece of glass that Newton used 350 years ago? And we can. We take the idea of Young's double slit and we say the problem with Young's double slit is there's only 2 of them. If we had 1,000 of them, we would have much more light intensity. And so we do this trick with that. And that's interesting. There's a lens there, and yes, but we do a lab where we get a lot further away. This is a very high magnification of the lens of the so-called diffraction grating. And on this scale, you can't, if you drew it and the screen was there, they'd never meet. But like we've done in the past, if you go a long, long way away, then you can pretend they meet. And so we can do this experiment by just having a light source, a diffraction grating, and a human eye. And we can actually measure some chemistry. And that's the lab that we do, I think, next week. That's the lab we do. It's a very nice lab. Anyway, so what happens is we say each slit produces a diffraction, and the diffraction beams interfere with one another to produce a final pattern. The condition for the maximum is that d sine theta equals m lambda. We've been here before. And don't worry about this. I don't care about the resolution, but get the idea. We have a light source, different colors of light come through. We have a diffraction grating. We can use this telescope and see what's going on. And so did I do this calculation last time? I don't remember. Let's do a calculation. So I'm going to take one color of light. Let's say we have 400 nanometers wavelength. I'm going to take a diffraction grating. Diffraction gratings used to be made by taking steel and then scoring it with a tool in a whole bunch of lines. And then people realized they could just draw a whole bunch of lines on a piece of paper and photograph it with a film camera, and the film would be the diffraction grating. And nowadays you can just basically do the similar thing with a computer. It's got to be high resolution, but you can make a diffraction grating for next to nothing. So cheap it's untrue. The light should go straight, but what happens is it's going to be sent out to different directions. This is the first order. And this is the second order. And that raises an issue that actually was just brought up to me, and that is I have a homework question where I talk about the second order dark fringe on a diffraction pattern, and I meant the first order dark fringe on the diffraction pattern. I was a bit loose when I was working on this before. I was a bit loose on my language of what was first order and what was second order, and I knew what I meant, but I wasn't communicating it very well. So be a little bit careful about that, and I'll be a little bit careful about that as well. Okay. So if I had more colors, if I had red in here as well, the red might be at different directions. So I could look at the first order black and the first order red, and if I looked at these, I would see a dark background with a red line on it, and I would see a dark background with the other color on it. It's not black, clearly. Blue, I guess. I could do it as blue. So I can see these things with a little telescope. Actually, if I put my eye here, I can actually see them by looking at this diffraction grating. I can just see them. So I can measure these angles pretty crudely. just using my eye and a protractor. So I'd shine the light through and I would look and I would say, well, there's the red, there's the blue and there's the red, and I get my protractor out and I can measure those two angles. So I can measure these angles quite nicely. So imagine having a hydrogen lamp or a mercury lamp, whatever. I can analyze the light. Let's kind of stick with hydrogen. Hydrogen's got a relatively simple spectrum. It's not in the room. And basically so hydrogen has an inner shell, a next shell, next shell. It's called K, L, M, N, or P, Q, as many as you like. There's one electron in hydrogen, so the electron's down here in the ground state just hanging out. Energy comes in, excites it. When it's in the K shell, it has the right energy to be in the K shell. When it's in the L shell, it has the right energy to be in the L shell. It needed more energy, it got it from the interaction, the heat or the electricity or whatever. It doesn't want to be in the L shell. If there's nothing stopping it, it will go back down into the K shell. When it was in the L shell, it had enough energy to be in the L shell. When it was in the K shell, it had less energy. So it gives off the rest as a photon of light. Different energy separations give us different colors. That's why we get different lines, different colors of light for the hydrogen spectrum. More complicated atoms, the heavier they are, the more complicated the spectrum. But you can analyze it. You can recognize the pattern. Okay. We take a hydrogen spectrum, light comes through, it gets broken up into a few different rays, different colors. Let's pick one. I say for the first order, I don't know, 400 nanometer wavelength color. Say you don't know. So you don't know the number, you know. I can't do that because I'm going to get the wrong value. So forget that. Let's say we know it. Okay, what angle will that be at? What is theta value? What's the angle for that red? Yeah. I say, okay, m lambda equals d sine theta. So 1, because I said first order, it's the first red line, times 400. If I work in nanometers, I can leave it in nanometers because it's going to cancel. If I don't work in nanometers, I've got to convert it. Is equal to d. A typical diffraction grating is characterized as something like 600 lines per millimeter. They're very close together. But I want to know what d is. D is equal to the distance, 1 millimeter, divided by the number of lines, 600. So D is equal to 1 over 600 times 10 to the minus 3 meters. Yep. I'm in meters, so I've got to work in meters, times 10 to the minus 9, because that's in nanometers. And D is 1 over 600 times 10 to the minus 3, and that is sine theta. So sine theta is equal to 600 times 400 times 10 to the minus 9 over 10 to the minus 3, which equals 24 times 10 to the 10 to the 4 times 10 to the minus 9 over 10 to the minus 3. So sine theta is equal to 24 times 10 to the minus 9, take that 3 to the top, minus 6 minus 2, which equals 0.24. So theta is equal to, did I bring my calculator? I've always got a calculator on me. So let's have a look. We go second, I need a sine. Second sine, 0.24. And I look and I am in degrees, so I'm getting 13.8 degrees. Yeah. So you see what we did? We took m lambda equals d sine theta. We sorted out what our order was. First line away from the origin, away from the straight through is first. Second line, second of the repeat of the colour. It's got to be the same colour. So the first time you see red, m equals 1. The second time you see red, m equals 2. The third time you see red, m equals 3, because the pattern's repeating. Not very often, but it does repeat. We've got to work out our D, not our lines per millimetre. If I give you this question, I'm going to give you it in lines per centimetre or lines per millimetre. You've got to do the conversion. So you've got to be able to convert. And you've got to get lambda from somewhere. I'll probably give you a lambda. I could give you the frequency and have you work out the lambda from, you know, lambda equals speed over f, you know. But one way or another, you get the angle. You can predict it. Here's another thing now the other thing you could do is, in the lab, you could measure this angle experimentally, and then using this math, you could figure out what the wavelength is. Here's what you can do next. E is equal to HF. E is equal to H. F is equal to C over lambda. E, whoops, I didn't mean to do that, which equals H, which is what, 6 times 10 to the minus 34 or something? Sorry? 6.6 times 10 to the minus 34. C is 3 times 10 to the 8 over lambda. And lambda in our case was 400 times 10 to the minus 9. And if you work that out, can somebody work that out for me? It's going to be it'll be 4.9 times something.
4.95 times 10 to the negative 19
joules, which is a typical interatomic energy spacing. So let's think about this. We can go into the lab with a diffraction grating which costs about, I don't know, $5. It's kind of like the same material that if you go to the movie house and you look at the 3D films, they're using polarizing filters, which is the same kind of technology. It's the same kind of film. And they throw those away. I mean, they use them a few times, but then they ditch them. So you have a light source with some kind of hydrogen discharge tube, and you have a little diffraction grading on the table, and you use markers, and you find the direction, and then you just use, frankly, you just use markers and a protractor or rulers or whatever you want to do it, and you measure the angle. So you know the angle. So you can figure out what the wavelength of that color is. So you can figure out what the energy difference between those two energy levels is for the atom. You've just done atomic spectroscopy, which would have got you a Nobel Prize 100 years ago for about, not that much. However much the lamp costs, because the rest is free. It's really quite amazing that using something as simple as just this little diffraction grading, you can figure something as fundamental as the energy spacings between energy levels in an atom. It's just really impressive. And in principle, it wouldn't work because it's not sensitive enough in terms of light intensity. But in principle, you could take the light of a star and put it through your diffraction grating, and using the same system, you could work out what the chemistry is of the atmosphere near a star that's 5,000 light years away. You're in chemistry at a distance. It really is amazing. What optics and spectroscopy enable you to do is just kind of unbelievable. Yeah.
So you're saying if we weren't given the wavelength, we'd have to measure the angles?
Yeah, you got to have one thing missing from this equation. So my choice as your examiner is, I got to either give you the wavelength, and I could give you the wavelength and ask you for the angle, or I could give you the angle and ask you for the wavelength, assuming I give you D and M. They're the two things that I commonly play with.
How do you find the wavelength between the two? How would you find the wavelength, or that's the other?
I gave you that there. Okay.
Yeah, how would you find it if we didn't? If you weren't? Oh, never mind.
You'd measure the angle.
Okay.
Yeah. Cool. Okay, so don't worry about that thing there. Last bit, plane polarized light. So light consists of basically an electric field which is oscillating, and that is inducing a magnetic field which then oscillates, which induces an electric field which then oscillates, which induces a magnetic field which then oscillates, which induces an electric field which then oscillates, which induces a magnetic field which then oscillates. And after a while, who can remember who started this thing off? It was just one causes the other. And under that circumstances, because one causes the other, you don't need a medium. It's, again, quite shocking stuff. We know that light is an oscillation of perpendicular electric and magnetic transverse waves. Unpolarized light source, like a typical filament lamp, a typical old-fashioned light bulb, or the sun, emits photons with any orientation. What that means is, forget about the magnetic field, just look at the E field. If I look along this direction, I see this thing wiggling towards me like that. Well, that's one photon. Maybe another photon will be having that orientation. Maybe another one will be like that. 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 So there's going to be a variety of orientations for this electric field. Fine. Yeah, there's no law says. It's like throwing a football. Which way do the strings go? The laces go. I guess you're taught to spin it. But if you didn't know that, you threw it. Some people would throw it with the laces up, and some people would throw it with the laces at one side, and some people would throw it with the laces at the other side, and some people with the laces at the bottom. It's still a football. It doesn't make much difference. But if we could then filter the footballs based on the laces, it becomes quite useful. So can we filter the photons based on their orientation? And we can. An unpolarized light source can emit photons from any orientation. A linearly polarized, sometimes called plane polarized or simply polarized wave, contains wave with only one orientation. So what we've done here is we've said, okay, we're only going to allow through photons which have that same orientation. They can be separated in space. I suppose I should have drawn this like this. I should have drawn it like that, and that, and that, and that, and that, and that, and that. I mean, wherever. But in this one, it's there, and 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 there. They're all the same orientation. That's because somehow we've managed to polarize our photons. There's really two ways of polarizing your photons. One is you pass them through a polarizing filter, which really only lets through the photons or the components of the photons which have the right orientation. And the other way is you reflect them off a shiny surface at a certain angle, and they tend to come off polarized. One way or another, either nature does it or we do it on purpose. We can get a beam which is made out of photons which all have the same polarization. There are some materials which they're called optically active materials, and they can twist the polarization of a photon as it passes through. So I can have a piece of material, and when the photon begins, it's that, and then what happens is it kind of twists it. So by the time it comes out, it's like that. Well, maybe another grain of this material has a different orientation, and maybe it makes something go like that. It behaves differently. So I have this weird situation where different samples of these materials, they'll twist the light, but not to the same extent or not in the same direction or whatever. This becomes really quite analytically very interesting, because what I can do is I can take a plain polarized material, I can take plain polarized light, and I can pass it through a material and let it do what it wants to do. I can illuminate all of this. And when I look at it, what I'll find is that this bit was really well polarized in that direction, and it shows up really brightly. And this bit, well, I missed something out. And this bit is polarized in that direction, and this bit is polarized in that direction, and this bit is polarized in that direction, and this bit is polarized in that direction. So the light came in vertically, and it got twisted different ways in different grains of this material. If I just look at it in light, I can't tell that. It just looks like glass. But I put the plain polarized light there, and I put the plain polarized light in, and I'm still can't tell. But this is what I can do. You see, this polarizer is made of a crystal, and what it does is it's like having a picket fence. Imagine that you've got a skipping rope, and you're passing it through a picket fence. It will only let through vertical oscillations. Horizontal oscillations it won't let through, because they'll hit the bars of the fence. Okay, so I take plain polarized light. I take unpolarized light, and I put it through this filter. This filter has a picket fence that way. So the only thing that can get through are photons which are the same orientation. So I've just made my light plain polarized. I can then pass it through this material, which has made it jumbled. I then pass it through a second polarizer. And if the direction of the polarizer matches the direction of the light from the grain, that shows up as really bright. And this one down here, nah, not so good. This one's terrible. This one is completely wrong. So what was a transparent material becomes bright and dark and somewhat bright and very dark and somewhat, and so on. It shows the grains of this optically active material very clearly. So this is, and it's called by various terms. I've seen it in microscopes, optical microscopes, called Zemansky, I think it's Zemansky imaging. So you have a polarizer and you have an analyzer. In the absence of an intermediary active material, if I put the direction of my polarizer and the direction of my analyzer in the same direction, everything that gets through the polarizer will get through the analyzer because they're in the same direction. So can you see here, I'm not seeing much of a decrease in intensity in that middle bit, because everything that gets through the bottom one gets through the top one. If you do it in practice, there is a little bit of a fall off because there's more thickness of material. If I twist these things slightly so they're out of line, it's not that I get nothing through, but I get less through. So what gets through the polarizer, some gets through the analyzer. What we say is it's like a component. It's not that the ray goes away. It's that a kind of, if you like, if that's the one that's not lined up with the analyzer, we kind of take that and we say that amount of it gets through. So that's the full photon, and here's the kind of proportion of it that gets through. But it's not zero. But if I turn these things so they're at 90 degrees to each other, then, well, 90 degrees, if it's like that, then basically nothing gets through. So I can turn these two filters, and at different orientations I'll get different grains lighting up. So that's kind of interesting in its own right. Secondly, it turns out that stress can make materials more or less active. So if I take a piece of plastic, for example, and I stress it, I'll start seeing, and I put a polarizing filter in front of it and an analyzing filter behind it, I'll start seeing patterns of colors where I'm stressing it. So this is an optical way of showing stress in two-dimensional materials. So you can build the model of a hinge and say, where is it likely to break? By stressing it and looking at it through these things. So structural engineers kind of like this kind of technology for complex systems. So I need you to know terminology. First of all, unpolarized light, and then plain polarized light. I think it's spelt like that. And I need you to know about the polarizer, and I need you to know about the analyzer. So I need to know that language. I need you to know that there is optically active material, and it can twist the orientation of a photon's electric field. I need you to know that for a system like this, the intensity of the light that's coming through, this is low intensity, this is more intense, this is very intense. The intensity of the light that's coming through is equal to the intensity of the original light, Imax, times the cosine squared of the angle between the two filter orientations. So this would be a theta of 0. This would be a theta of 45 degrees, and this would be a theta of 90 degrees. And cosine of 90 is 0, yeah? That's Maulus's law. I need to know that. Yes?
So polarize and analyze, those are two different things, or are they like two sides of the same substance?
Oh no, there's one film here, and then a space, and another film there. And I can twist them relative to each other. Now, this is a bit technical. There are polarizing filters on displays like this. They make use of polarizing filters. It's a liquid crystal. You have light comes in and reflecting. It's plain unpolarized light comes in, is through one filter, gets polarized, and then it does stuff with it. So useful. When you go to the movie house and you look at a 3D image, they're showing two images on the screen, agreed? That's why when you take your glasses off it looks blurred. In a simplest way, if you have a red filter and a blue filter and you make your colours appropriate, you can actually look and you can see through a red filter and a blue filter, you'll see a three-dimensional image. Because only the red gets through the red and only the blue gets through the blue, so you see it. But the problem is it messes with your colours. You can't have very nice colour when you have red and blue filters. And the next level was, supposing that we shine one movie projector through a vertical polarizer, and we shine the other movie projector through a horizontal polarizer. And then I wear a vertical polarizer on my left eye and a horizontal polarizer on my right eye. Then I got a screen with two images, and this only sees one of them and that only sees the other one. And I can see three-dimensional effects. And that's the first 3D using polarizing filters did it that way. If it's not perfectly lined up, it tends to not be so good, and people tended to get headaches with that. People would complain about, 3D, it gives me a headache, you know. So when you go to the movie house now, they have polarizing filters, and I think they're more sophisticated. I think they're what's called circularly polarized. And I don't really know what that is, but it's a different technology. It works better because you can tilt your head and it's not so. If you tilt your head slightly and then you're no longer lined up well and all that kind of stuff. Okay, so it would be useful for movie houses. What really got this stuff to become popular was sunglasses. Back in the day, back in the, 30s, who was it who invented sunglasses? I've heard it was Benjamin Franklin. I'm not sure if that's true or not. Apparently he was walking through the streets of France, and French have wine bottles that are not the only people, by the way, lots of people have, but it was coloured glass. And he thought, I could make lenses out of these coloured glass, and then I could wear it, and I'm not sure that's true. If only because, how often is it sunny in France? No, it's not. It's just, I don't know if that's true or not. But all that does is it colours the light. If you have blue tinted glass, it lets through the blue light and keeps the other colours out. It kind of rejects colours. It can be quite effective. The first time I came to the States, I was in New York, and I had a pair of very light blue sunglasses on. And after a couple of days, my buddy said, "Let me have those sunglasses." And he put them on, and he goes, "Man, this is cheating." He said, "It makes the city look really clean." And it did. When you had these on, it looked really fresh and everything. You took them off, and it was like a bit. It was back in the 70s. It was a bit not as nice as it is now. But again, you're just changing the colour. You're rejecting some colours of light. And if it's a very bright day and you want to reject lots of colours of light, you have very dark glasses. Well, the problem with dark glasses is you go into a room and you can't see a thing. You're driving and you go into a tunnel, you can't see anything. A tree goes over the top, you can't see anything. It's like, it's a real pain. And then people found that there's a thing in nature whereby sunlight, when it comes down and is reflected, now we have the reflected ray, we have the reflected ray, and we have the refracted ray. It turns out that if I come in, so look at these angles of incidence and angles of reflection. So angle of incidence, angle of reflection. And what we find is when unpolarized light is incident on a reflecting surface, the reflected and refracted beams are partially polarized. When you come in at a larger angle, you can get to the stage where the reflected beam is completely polarized when the angle of incidence equals the polarizing angle. And this is sometimes called the Brewster angle, and this is Brewster's law. So if I come in at a shallow angle, well, a big angle actually, but grazing the surface, I can get light coming off, which is then, it's not got a limited number of orientations, it's only got one orientation. If I'm looking in that direction, I just see these rays of light coming in at me like that. Here, I'd see, you know, but not all of them. It wouldn't be the vertical ones. It would be, they'd be missing, but these would be there. But when it comes in below the Brewster angle, you get in nice polarized light. And that's different from the photons coming directly into my eye. So only the reflected photons will have this polarization. So for instance, if you have a water on a surface, like after it's rained, the sunlight that comes down that bounces off the surface would be polarized. Or if you buy a lake or a pond, the sunlight that comes down that reflects off the surface of the water would be polarized, provided that the sun was kind of low. Oh, if I make my sunglasses like that, I can reject those reflected rays while still allowing through the normal sunlight from other sources. And those reflected rays tend to form the glare. If you look at the cars in the car park, I can see glare from the back windows of those cars. That light is polarized. So if I can make my sunglasses to reject that polarized light, I'm just getting rid of the glare. I'm not particularly getting rid of any of the other light sources. So it's not that I can't see. If I just use dark glass to get that glare down so it's not glaring, everything else is just lost. But this is a clever way of just getting rid of the glare. And so people would go fishing. This is where they first got, it was military first. And then after that, it was like sports people. And they would say, hey, you can see the fish in the pond. You know, and it's like, and then pretty soon everybody has it. So, well, not everybody, but. So initially, polarized lenses, Polaroid was like the name, trade name. And then after a while, other people could make polarized lenses. So you got polarized lenses. And there was this thing about it's not Polaroid, it's polarized, you know, it's like not as good quality or whatever. And in fact, there were so many knockoffs that if you bought a set of polarized lenses, they would give you a little tag with a little bit of polarizing film in it. And to check it, you were supposed to twist it. And if you twisted it, if it was true Polaroid or polarizing lenses, then as you twisted it, you could make the orientation go so it would be a dark and then light. You could twist it and you could see that dark and light coming. And if it wasn't, if it was just a knockoff, then that wouldn't have the effect. And they wouldn't give you the film. That was the other thing, you know. So, So it became incredibly popular. And, you know, I don't know what you guys feel, but to this day, you know, polarizing lenses cost more, but they just seem a bit easier on the eyes as far as I can see. It's like, I prefer them, but they cost more. That's the issue. Cool. So for this, I need you to know, so what does this say? N is equal to tan phi. I don't really. So it depends on the refractive index, I guess. And that equals tan phi. I don't care so much about that. I'd like you to know it's there. I really care about that. I really care about that. I really care about that. So, question or comment? Yeah.
Regarding that refraction.
Oh, I better do that quick.